The outline of the talk will be the following. At the beginning we will review a bit the importance of the strengths of the phase transition in the standard model, and we will see that in the standard model it is enough, it is not enough, and so it's a good idea to enlarge the standard model to, for example, the MSSM. In particular, we will consider the parameter region of the MSSM where the stop is very light and some scalars are heavy, and for this reason it is necessary to obtain the effective theory of this model, and in order to do that we will have to produce the magic condition at the scale at which the heavy scalars decouple, and the renormalization group equation in the effective theory. Once we have obtained the effective theory, we will be able to understand the light Higgs and light stop masses predicted by this scenario, and we will study the electroweak phase transition, the windows of the parameters in the parameter space where the phase transition is strong enough. We will see that this parameter region is compatible with gauge coupling unification, and at the end I will give some conclusions about this part. After, running against the time, I will speak about a manner to obtain a strong first-order phase transition in 5D models. So let's start. Björn told us yesterday that the universe is matter-dominated. In particular, we have Big Bang nucleosynthesis and the cosmological microwave background, giving this number that you know. And for this reason, since we expect that at the beginning the universe was matter-antimatter symmetric, we have to find a mechanism working at some moment between the beginning of the universe, at the beginning of the universe and today, in order to produce this number. It was realized by Sakharov that any mechanism attempting to do that has to contain this three conditions. It has to violate the baryon symmetry, the B number. It has to violate the CNCP symmetry, and there has to be a departure from the thermal equilibrium.
Sorry, where does that number come from? I mean, I have seen various numbers. I haven't seen this number.
It
looks nice.
It's a nice number. What did you? I mean,
I think that it is a partial data group.
Oh, okay. Sort of combining everybody's good.
But I think that
guesses. Yeah. Okay, it's a nice number.
So it was a surprise, at least for me, when it was understood that the standard model almost already contains all the Sakharov conditions. It has there is the number violated by processes at finite temperature. We have here a picture of the event. The standard model contains also the CP violating phases in the Kabibov-Kobayashi-Mascava matrix, and moreover, it is possible that the electroweak phase transition is first order. And in this case, we are able to obtain a departure from thermal equilibrium. Oh, thank you very much. Okay. Wonderful.
That was quite short.
Yeah.
I think you deserve the first prize for the talk.
Okay, thank you very much. Okay, now okay, so you already know first order phase transition means that the Higgs effective potential has to have this behavior, which means that at high energy, the minimum of the electroweak symmetry, the value of the BEV, the BEV of the Higgs is in the origin, therefore we are in the symmetric phase. After, by decreasing the temperature, another minimum appears, and at the critical temperature, this minimum is generated with the other one, and there is a temperature at which the nucleation starts, and some bubbles appear, and they will expand, and in particular there will be a temperature at which all the bubbles fill the universe, and the transition is ended. The important point here is the size of the barrier, which is given by the trilinear term here. Pay attention to that, because after we will have to come back to this point. So, you told me that in front of the bubble there is the SCP asymmetry. For this reason, the movement of the bubble, okay, you know all that better than me. But there is the asymmetry between Q left bar and Q left. The sphalerons are more frequent for the events erasing Q left bar, simply because there are more Q left bar than Q left. And for this reason, temporarily in front of the wall, there is a baryon asymmetry. After there is
You should actually put the minus in between there.
Are you sure? Because
It's the axial current that gets sourced.
okay, sorry. Yeah, okay. I will. The point I think that what is important here is to say that there are more Q left bar than Q left. Okay, and in this manner, the sphalerons erasing Q left are more frequent, simply because there are more Q left than.
Yeah, but you just wrote the
The correct part. Sorry. So the baryon asymmetry is introduced by the movement of the bubble, and inside the bubble now we have produced a baryon asymmetry, but this asymmetry will be washed out if the sphaleron inside the bubble is active. In order to understand if the sphaleron is active or if it isn't, we have to study the effective potential of the Higgs, and in particular we will see that if this condition is fulfilled at the moment of the nucleation temperature, the rate of the sphaleron is smaller than the Hubble rate, and in this manner inside the bubble the sphaleron is switched off. So, repeating, it is extremely important to understand the value of the Higgs wave at the moment of the nucleation temperature.
Sorry, what are these different lines? What is the red one?
This one? And this one is the sphaleron rate before the electroweak breaking.
Ah, okay, and then you
This
say...
is the scale.
okay, there it's fast, and then, yes, and the temperature decreases,
Yes.
and then the rate gets
Temperature larger than this
yes,
one.
okay, and then the other,
This part,
yes,
and this part is in this case. Okay. This damper is due to the fact that here, at this moment, there is the electroweak breaking. So, after you have to use the other sphaleron rate, sphaleron rate in the broken phase.
you say that the red one really is the symmetric phase?
Yes, symmetric phase.
Okay,
Here,
and then you say,
there is
okay,
the
and then
break.
you have a
There is a
much stronger damping.
Yes, it's
because of-
continuous.
So 10 to 12 GeV, the sphalerons becomes stronger than the expansion rate. So
Yes. Yes.
that's what the plot says.
Yes.
Yeah. And it is the reason for which models producing the baryon asymmetry beam cell at the beginning of the universe. Okay.
No, it's nice, but I've never seen it. That's what I'm asking. Oh, good.
So, qualitatively, the standard model contains all the ingredients, the Sakharov ingredients, but we are unlucky because quantitatively the things go bad. In fact, it was discovered by Lax's calculation and many other calculations, a lot of stuff, that for a Higgs bound, for a Higgs mass larger than the present Higgs bound, the phase transition in the standard model is a crossover, therefore there is no phase transition at all. So, okay, it was the introduction, but now, okay, you already know that it is. Here I would like to stress that if we change the Higgs effective potential, we can obtain a stronger phase transition. And a point that I have not mentioned here is the problem of the CP asymmetry. But when we enlarge the standard model, typically we can obtain naturally new phases breaking the CP asymmetry. Therefore, what we are going to do here is to enlarge the standard model and considering his minimal supersymmetric extension. It was previously done, but a lot of people, but it was done around at the end of the previous century, which means 10 years ago. And they discovered that in the MSSM there is a parameter region where the phase transition is strong enough. This region was dubbed a light stop scenario because the lightest stop, which is mainly right-handed, is lighter than the top. But when they analyzed this window, they had another X mass bound respect with the present one, which was this one. For this reason, we are not sure that their window is correct today. But another important point is that they discovered that for a large CPO X mass, the parameter region where the transition is strong enough can be translated in a window of the top mass versus the X mass. Now the problem is that they considered a window for a value of MQ, which is the left-handed stop mass of few TV. And in this case, the window is duplicated by the present of the present X experimental bound, because they calculate everything with this bound. And moreover, they calculated the windows for X mass calculated at one loop, and the one loop approximation is a bit optimistic respect to the two loop one. So, okay, sorry, it was a talk. I have recycled something. Okay, but so we wanted to understand what happens to the windows whether we increase the value of the left-handed stop. And in order to answer to this question, it is not so obvious because they calculated the X mass for at one loop. And in this case, if we increase MQ, we obtain large logs in the calculation. And for this reason, the value of the X mass is calculated in this manner is not reliable.
So, so you're saying this, in the end you compute an effective potential, which probably has temperature zero and temperature dependent parts, and the temperature zero part didn't include two loop
when they
did that at that point, because then you could, well, at least this would give you some would at least contain some of the two loop terms in the
they considered the two loops approximation, but only
on the term.
Temperature. So the problem, I repeat, is if we consider large MQ, which is the manner to attempt to increase the X mass, we obtain large logs. For this reason, we have to calculate the effective theory of this model. In order to do that, we focus a bit on the spectrum. We have fermions at the electron scale. Gluino can be a bit heavy, but in our case it is always close to the electron scale. We have the right-handed stop, which is lighter than the top quark. And for simplicity, we consider that all the useless scalars, the heavy scalars, have a common mass, which is called m tilde. And as we will see after, we will observe that this value has to be much larger than phi TV. Finally, for the strength of the electroweak phase transition, we will have to consider a trilinear coupling term smaller than m tilde. And in other words, we are considering a sort of light stop scenario in split supersymmetry.
Yeah.
So the idea is to decouple these heavy scalars and to obtain the effective theory. In order to do that, okay, the idea is the following: at very high energy, supersymmetry is a good symmetry of the model. And for this reason, for example, the interaction of this interaction has the same coupling constant as this interaction. But by decreasing the energy, we arrive to the value m tilde at which the heavy scalars decouple. And for this reason, this value start to be different, because supersymmetry is not a good symmetry of the theory here. So at below m tilde we have the effective theory, and we have to match the effective theory and the fundamental theory at the scale of decoupling. In fact, at this scale they have to represent the same physics. Once we have matched the theory, we have to run down the effective couplings known at the scale m tilde up to the electroweak scale. When we consider heavy gluinos, we have to repeat this procedure, the matching around procedure, also at the coupling M3, at the energy M3, which is the gluino mass.
This parameter lambda, I mean the quartic of the hits?
Yes, this one, yeah.
I mean, usually it's also related to the G's, no?
Okay, this is the effective theory, and so it is related to the G's only at the matching condition, at the scale. But
you take also into account the running in...
Yeah. Yeah.
Why?
Yes.
Why is the gluino mass smaller?
Why it is smaller? Because the idea is that, for example,
Otherwise, if you remove all the gauginos from the.
no. The genos important for for example, for the baryon asymmetry.
Yeah, that's why. I mean,
are at the electroweak scale. I'm speaking about gluinos.
Yeah.
And the gluino is not important for.
No, but M3 isn't that the gluino mass?
The gluino.
Yes.
The gluino mass. The important parameter are the charginos, no? And for the baryon for the production.
That's why I don't understand. Why do you pick the gluino mass to be smaller than the other stuff? You could also make the gluino heavier. I'm saying.
But then a reason, because typically you are thinking that, for example, there is a parity. The chiral symmetry for which the fermions are light.
Okay, this point comes from
this
compromissive split supersymmetry.
And for example, when you study unification, you would like that the gluino is more or less of the same order of the other gluino. No, the other,
gauginos.
yeah.
So what is this notation? TR omega, TR gamma?
And this is the color, the index of the color. If you want, okay, forgetting about the color, it is a modulus t squared to the 4. To the square.
So you do it in one loop?
Yeah. Now you can see.
The construction of this effective Lagrangian in one loop.
Yeah. For example, okay. For example, what to concern the quartic coupling of the X, we have to match when we match it. We have to match the effective coupling, the effective theory, and the fundamental theory, and we do that at one loop, without considering non-normalizable operators, and okay, the method bar, dimensional regularization, and okay. Okay, this manner, for example, we obtain the threshold, which is the. Okay, in this manner we obtain the matching condition for the quartic coupling of the Higgs, and this matching gives the threshold delta lambda, which is the vertex of the proper vertex. In the same manner, we have also to match the propagator, and in particular for the X, we have to perform this matching, from which we obtain a threshold to the wave function coupling here, this threshold. This is the case for the quartic coupling, but clearly we have to repeat everything. We have to repeat this procedure for all the effective couplings. In this manner, observe that these matching conditions are correct only at the scale of the coupling. For this reason, okay, Thomas, you have the answer here, no? Yeah, you have the answer here. Usually, when you don't consider the decoupling of the particle, okay, you don't consider the line at below m tilde, you have this one, where delta lambda is, in the case when all the two stops are heavy, have the same mass, you obtain the typical threshold. Okay, so I stress these matching conditions are correct only at the coupling.
So what are these delta, lambda, etc.?
Delta. They are the proper vertex thresholds. And these ones are the wave function thresholds.
And you will show those?
No, here no. I calculate it. If you want, after we can speak about it.
Just
Okay.
contributions.
Yes, at one loop, except this coupling, this threshold, which comes from A3 level matching. Yes, because it is this coupling is the effective coupling between the two stops and two X. In the fundamental theory, you have fluoridic,
So this is because the two stops mix with each other, probably.
yeah, because any art, okay,
Mm.
you have here, stop, for example, in Higgs, and here you have the mix in it.
Yeah.
So, and this one is the left handy stop, which is heavy. So at the moment of the decoupling, you have to contract it.
And that's the model.
Yeah. And this is the unique threshold coming from a three-level contribution. So, after we have to calculate the running in the effective theory in order to obtain in order to run the effective couplings from the scale of the coupling m tilde up to the electroweak scale. Okay, this is the
These are one, some of them are two.
no, all they are
All one.
one loop beta function. In particular, when we run below the scale of the gluino mass, the coupling G have to be erased because it doesn't make sense to consider them. The gluino is decoupled below M3. And okay, the same thing for the masters. They are correct because you can perform the supersymmetric and supersymmetry limit, and you can check that these beta functions seems correct. Okay, not they are correct. Maybe, if you want to check. Okay, but the important thing, in order to summarize a bit, is that in this theory we have some experimental inputs at low energy, the electroweak scale that we fix at the top mass. After, these are the experimental inputs. After, we have some theoretical inputs, which is, for example, the mass term of the Higgs, because we are fixing the one loop effective potential in order to have the minimum at 246 GeV. And by the matching conditions, we have the matching conditions that are correct at the scale m tilde. After, we have other free parameters, these ones, which we fix at the electroweak scale, and parameters that are present also in the fundamental theory, these ones. And the effective couplings will depend on these values, which exist only in the fundamental theory. So what we have to do is to run up the values at the low energy. We have to run them up to the m scale, m tilde scale, at which we perform the MHC condition, and after we run down the effective couplings. In this manner, we have resumed all the large logs. All is we have leading logs. Okay. In this manner, we have obtained the effective theory where the large logs are summed in the effective couplings. In this manner, we can calculate everything for what concerns phenomena at the electroweak scale, in which the large logs are summed. In particular, we can calculate the X mass, and in this case, the calculation is reliable also for large value of MQ. In this manner, we have solved one of the questions we have put up before. Oh, thank you. It was time for questions today. It is what we can produce, the prediction of the model for this value of mu squared, which has to be negative. After I will remind you the reason for which it has to be negative. These are the X mass prediction for the several value of tangent beta, and these lines, the dashed lines, are the stop mass. In this case, we observe that for this value of m tilde, the thermomixing is forbidden by the left bound on the X. The situation improves if we consider a larger value of m tilde. And in particular, we can observe here that if you want electroweak baryogenesis, which means negative values of mu squared, this condition, we have to focus on this plot. And if we want, for example, for electrodipole moments bound, to consider value of tangent beta smaller than 5, and we want to consider a value of m tilde smaller than 10 TeV, the situation is very, very bad. So we can intuit that here we have an Higgs mass bound, which is below 133 GeV, and an upper bound on the stop mass, which is 112.
This is on the right-hand side, yes? I mean, with this M12 equal to 1000 PeV, or?
Sorry.
These bounds, they come from which?
The
M12.
This one.
So what is M12 then?
This bound comes from, you can accept any value of m tilde.
Yeah.
Observe from this plot that this linear mixing equal to this value more or less is the maximum allowed by the stop bound mass. So, and accepting this upper bound on linear mixing, you can obtain the maximum value of the X for the given m tilde. After, if you plot this maximum allowed X mass versus the m tilde value, you obtain these curves.
Hang on, what's the maximum allowed in order to do what?
Okay, in order, if you accept this value as an electroweak, but after we check better, it is if you accept this value and now and you accept this bound on the linear coupling, you observe this value comes from this point, and the stop value, this bound. And now you answer your question.
I mean, there's some criterion for something which I do.
Yeah, okay.
This is for fixed AT, right?
Yeah, this one. Yeah.
Fixed
Well,
AT?
this bound here that you.
No, that's the maximal. It seems it's the maximal mass you can get once you fix mu squared. Yes, because what you would normally like to do is you'd like to increase the stop mixing.
Right.
Yes, but
Maybe,
this
yeah.
gives you a bigger Higgs mass. But when you fix the right-handed stop mass and you increase the mixing 2 by 2 matrix, and increase the off diagonal, then of course one of the eigenvalues gets smaller and smaller.
But he's fixed this to 0.5. No?
Yes, but suppose you can completely neglect. You know, suppose you have a mass matrix which has a 0, yes, and another diagonal, another off diagonal. Yes, and of course you get one small, or potentially negative eigenvalue because the other term is not 0 but negative. Yes, so to escape that, what you would need to do is to make the Higgs mass bigger, you must make mu squared bigger. Then you can allow for even bigger mixing, and then I guess what can you reach something like 160 or so in the if you
Then squared.
if you make everything. I think it was in the split SUSY limit when you make everything heavy.
Yeah.
Do you remember?
Yes. The
Something like 160.
100, yeah.
Something like 160
Yes,
or
yes.
so.
So what does that have to do with baryogenesis? Sorry, you said this has to do with the phase transition then somehow.
No. In fact, it is a previous result. After now
Now comes the...
to the yes the part. Okay.
Okay, so but you didn't answer the question of mu squared. I mean, if you make it bigger, then what happens?
Well, that's what comes now, I suppose.
Okay. For most variation of mu square, the Higgs mass doesn't change, but the Higgs mass, the stop mass, does. Okay.
And why would I... So this thing at the bottom, these two criteria, why would I want those? If there's something I would very much like. I mean, m tilde less than 10 t, etc.
It is because typically when you calculate before, okay, in the previous world,
Yeah.
they were calculating everything, the windows, for a value f tilde
Right.
of 2 TV.
Okay.
Okay, so you can observe here that we have, by the improvement of the calculation,
Mhm.
we have increased a lot the value of the stop, left-handed stop.
Okay, so you calculate for 100 and for 1,000, but you actually calculate for everybody, all the way down to...
Here,
Is that down there?
here.
Is there? Okay.
Sorry, it is 10 to the 4.
10 to the 4?
Yes.
All the way to 10 to 12.
Right. Okay. So now you're gonna... But now you're saying baryogenesis is difficult because...
The Higgs mass excluded.
Yeah, this is, I guess, it's a problem anyway, because what you're saying is that you don't get a big enough Higgs mass,
Yes.
which is not just difficult for baryogenesis.
Okay,
but
so it's generally... You cannot get a
But,
Higgs mass that's large enough. with
Yeah.
This, irrespective of
It's
baryogenesis.
just difficult within the MSSM.
Yeah.
Okay.
Mainly if you accept that you have to have
Yes,
these
this is-
negative values.
yes.
Right, so you could down you could scratch out plus electroweak baryogenesis, and it would still be difficult.
Yes.
Well, but you could. No, but if you wouldn't have electric baryogenesis, then you could make mu squared big.
Right.
Yes.
In this case, we have no problem with about.
Okay, and then you could escape this
Yes.
if you would go sufficiently high up.
Is it already in the ring where you have this quasi-stability against a kind of a colored phase? I mean, there's this recent paper here also of your colleagues.
Sorry.
I mean, they claim that if they allow not absolute stability of the Higgs phase, but it could be metastable, yes?
Yeah. Okay. Now I'm going to this point.
Oh, yeah.
It was only a previous result because if you use effective theory, okay, and we look at that the Higgs mass and the stop mass and the parameter space, more or less you can intuit that the things go bad for a value of tilde small, very small. Okay. And it justifies the fact that we have to consider effective theory in order to analyze this problem. So, finding a negative value of m squared. Okay, at the beginning I told you that it was necessary a potential of this kind, for the Higgs mass, and in particular it was important this value, the linear coupling term, because the size of the value depends on E. In particular, in the case of the light stop scenario, we have only a new particle contributing to the effective potential, to the barrier of the effective potential. You have to remember that only scalars contribute to the barrier. Only scalars have a contribution going in this manner, okay? And in this manner they may contribute to the trilinear term. In particular, for the stop, we have exactly this contribution, and we observe that in order to obtain a linear term, we need a cancellation between m squared and the thermal mass of the stop. Okay. In this case, we have optimized the size of the barrier, the contribution of the stop to the size of the barrier. But if you observe, we have to consider a negative value m squared. And in this case, we have the electroweak breaking minimum, the usual one, but we have also another minimum, which breaks the color symmetry. Okay, therefore, now that we have two minima, we can start with the universe at very high temperature and to decrease the temperature. And we can observe that depending on the value of the minima at the nucleation temperatures of the transitions, we can obtain an history of the universe ending in color breaking phase, into the color breaking phase or the electroweak breaking phase. In particular, if the nucleation temperature of the color breaking phase transition is larger than the electroweak 1, and the X potential in the stop, the color breaking minimum is stable, okay, the universe will end into in a minimum where color is broken, and so this possibility is ruled out. Another possibility is this one, in which the universe goes into the color breaking minimum, but this minimum is metastable. Therefore, if after it is possible a tunnel from for the color breaking minimum towards the electroweak breaking minimum, okay, this possibility is fine for us. But Klein observed that this tunneling is not possible, in the sense that the lifetime of the color breaking minimum, in this case, is larger than the age of the universe. For this reason, in this possibility, the universe, at practical level, ends in the color breaking minimum. Other two possibilities are these ones, and this one implies that the universe goes into the electroweak breaking minimum, and this minimum is stable. This possibility is correct. After, we have a possibility in which the universe goes into the color breaking, the electroweak breaking minimum, and this minimum is metastable. In this case, we have to check if this minimum is stable or is its lifetime is larger or smaller than the age of the universe. So, in order to study that, we have to study the stop, the Higgs and stop effective potential at two loop, because the two loop contribution at final temperature are important, where we consider the effective potential in the effective theory, where we consider also the effective couplings similar to G strong and the Yukawa one at the scale of the decoupling, which means that, okay, these ones are the most important parameters for this study.
So can I ask
sure.
back another one back?
Yes.
Sorry. So M is, so in that M is positive, E is negative?
This one?
Yeah?
A is negative.
M is negative. For a metastable.
No, it is, if you erase this part, it is the usual effective potential, X effective potential of the standard model.
If it's positive or negative depends on the temperature.
Yeah, but
Yeah.
I mean, the temperature where you nucleate M is positive, E is negative, lambda positive.
Yeah.
Yeah. Yeah.
Okay, so E is what? E is negative.
Yeah.
It always has to be negative, otherwise you don't get.
Right. and it's some power of something else. Right?
It's not minus sign, it's minus.
Okay.
So E negative gives you second minimum.
Right. Yes. Okay. Yes.
It's
got it.
negative, and
So
it
E-
has to eat up the temperature term. Yes?
So E is basically Q to some power.
Oh,
But you can also
no,
make E
good.
positive and then you have minimum on the other side.
Yeah. So E is basically Q.
E is Q.
If M squared is minus.
yeah.
Yeah, E is temperature times some combination of couplings.
So Q is, okay, this is not,
I mean, if I
No,
No,
okay.
no.
There
no,
is
this
a-
is just
a
pi
depend-
at critical temperature. So they're not. Now you say mu squared is approximately minus pi of t critical.
Yes.
But plug that in up there, but then it's not pi t critical, so it's not just q left. They don't cancel. That's my. I put that up there, then the pi's cancel, but they don't. Only t critical. And then E is q to 3 pi.
yeah.
No, yeah.
You see, if they didn't cancel at the critical temperature, then you would not have a big effect on the critical temperature.
Fine, I'm just saying that E is then basically q.
It's proportional to Q.
Yeah, to some power.
Yes.
Okay, that's what
There is also a contribution coming from the standard model, but it is small. Therefore, yes. Basically, E is proportional to Q.
So what you did so far is you improved the computation of the temperature zero potential, and now we add some
I also define a temperature in the fictive theory.
Yes, but so far you were talking about mostly the temperature zero potential.
Yes, when I put, yeah.
And actually there is Sven Heinemeyer would love what I'm saying now. That of course they computed the Higgs mass at 2 loops, or these people in Karlsruhe, so Hollig, I guess, Heinemeyer, Weiglein. And have you compared your result with the Higgs mass with theirs? Of course, I guess
Okay,
their
okay.
computation
When-
probably
when I-
have problems when you have large hierarchies, but on the other hand,
More or less, the behavior of the predictions are similar, but there is a practical problem, which is my fictive theory doesn't work very well when M tilde is small.
yes,
That the calculation.
best doesn't work very well when M is large. So is it then also? So how big is the kind of, because the 2 loop contributions basically bring the Higgs mass a little bit down. So the 1 loop gives this big increase, which you needs to jump over the Z mass, and then the 2 loop one will really bring it down again. So is it a future EV or?
Yeah, true there. Yeah. Now I don't remember exactly, but it will be a
Roughly.
thing.
But of course, since one is-
if you tell me 4GV, I tell you.
Yeah.
Okay.
And since of course one is anyway in this region where future EV really matter.
Yes. Yeah. The problem is that the window is supersized only
Yeah.
for a few GVs. Okay. So for this value f in tilde, we obtain this window. And in particular, okay, this line, for example, is the inside this window we obtain the strong effect transition. In order to produce these windows, we have to consider some cut. One is due to the condition tangent beta. But here we put this condition. After we will see why we have to impose tangent beta smaller than 15. And there is another cut due to the fact that we have to impose that the universe goes into the electroweak breaking minimum.
Oh, wait, I mean, you have the condition 0.9. and
Yeah, okay. In fact, it is at the
you are
critical
more used
temperature.
to 1 and 1.1.
Exactly. In fact, after we will check also this condition, we can see that in our case, for this value, at the end we arrive to, okay, in order to obtain a strong first order phase transition, we need this condition larger than 1, but at the nucleation temperature.
Oh, okay. So that's a little bit bigger then.
Yes. these are the windows we produce. In particular, I think that people are interested in knowing the behavior of the maximum of the maximum X mass versus the value of m tilde, and this is what we predict. In particular, we can see here plus minus 3 GV, which is the error of an estimate of the error of our calculation translated in an error of the Higgs mass, which corresponds to this line. And the corresponding stop mass is this one. Therefore,
the stop is really close to being discovered.
Yes.
And what about LHC? Do you know?
Yes. Now or after? Maybe after.
You're gonna tell us, or?
Yeah. Okay. The problem is for example, Tevatron and LHC are hadron colliders, and for this reason, the main channel to discover the stop is by jet. The problem is if the neutralino and the stop are close, more or less, if their mass is different mass is smaller than 30 GV, LHC and the main channel analyzed by LHC and Tevatron cannot discover the stop. So there are other possibility, which is the gluino condensation, gluino fusion. In this case, there is if the neutralino, the lightest neutralino, and the stop have a mass larger than 5 GV, so the difference between them, yes. In this case, LHC will be able to discover the stop. If the mass is smaller than 5 GV, okay, there are many work in progress, and because there is the possibility of the photons, okay. I would say that if the difference between the neutralino and the stop is of 5 GV, there will be problem also at LHC. And observe that in this case, when the difference of neutralino and stop is of the order of 20 20 GV, we are in the case where the neutralino gives the correct relic bond for dark matter.
Also, I guess the upshot is that by not finding a right stop at the collider, you will not be able to rule out this scenario. Because there's always this kind of back door it's just that all you have that it appears, but it's a very soft one, so you must just not see it.
But when some people are working with this, right?
Yeah.
Maybe you never know. Maybe people will exclude that window.
If you find if you get a very soft particle, I guess it's difficult to find.
Yeah, the problem is at the end I don't know the statistic, in the sense that maybe it is faster to find the lightest Higgs, and to rule out the scenario if we discover heavy Higgs. Okay, no, yeah, you're right. In any case, there is the manner to avoid if you discover a Higgs in the windows and you don't discover the stop, in some sense you can consider that the windows are allowed.
I wonder, this Higgs bound, does it depend on the middle, as far as I remember? Yes, I mean, if you have a very big twiddle, yes, in this figure, and then you get this bound, but a smaller end twiddle, it's about as weaker, isn't it?
Yeah, I agree.
It goes down, yes, so
in fact, we can obtain these upper bounds in the case of m tilde extremely large.
Yeah, exactly, yes.
For m tilde smaller than 7 TeV, the scenario is ruled out.
Yeah.
But now, MH has gone down. I mean, it was 130 something, right? It was 133, and now it's, or is it different age?
No, it is smaller now because we are considering.
Why is it not smaller?
Because before it was an intuitive analysis. Okay. Now we are considering exactly.
Now you also include this.
We are playing with all parameters.
Southern bound.
Yeah.
Is that that's the new ingredient?
Yeah, but there is the bound on tangent beta, for example. But also, for example, in this case, the maximum value of the x, this point, is not obtained by a value of the trinomial capital term equal to dot 5.
Sure. Okay, I understand. And this small h is the same as big H.
Sorry.
You have a nh small h.
Yeah. Also the stop is smaller than before, or of the same order.
Okay,
Yeah.
fine.
Yeah. Okay. Moreover, if we analyze the minimum, the Rubik minimum, we discover that we are in the case where this minimum is metastable. For this reason, in order to consider correct these windows, we have to check this condition, this condition, and to check also that the minimum is stable, in the sense that its lifetime is larger than the age of the universe. For what concerns the first condition, it comes from the ADM's bound. For a value of m tilde equal to 10 TeV, we have this bound given by mainly by Chargino contributions at one loop. And okay, now I know that this is a problem. If we consider approximation in order, if we calculate the baryon symmetry produced by this approximation, these considerations, okay, we obtain this plot, and in the same manner we obtain a bound on an upper bound on tangent beta of 15. I would say that I know that you have many, the results can change a lot, okay? Well,
A bit.
yeah. But in any case, if you want to consider a smaller value of tangent beta, for example, you have to cut the window at this point. This line was obtained by cutting for tangent beta smaller than 15. This line is for tangent beta smaller than 5.
Sorry, sir.
Yes.
Okay, so the 2 is basically vacuum stability, and one is, yes, that's what you write there, huh? Number 2.
Yeah,
is,
the 2. The 2 is that at the nucleation temperature. So the nucleation temperature of the color breaking phase transition is larger than the temperature at which the electroweak phase transition ends. Okay? Okay, so the condition 1 is after we can check the second condition, because we cannot calculate the final temperature of the phase transition in any points of the window. So we have to use this approximation, and we check it for this value. And we discover that I'm running out of time. So, for example, the behavior of we start here. We will have the action of the bubbles, electroweak breaking bubbles and color breaking bubbles. Here we will plot here, and here is the Higgs effective potential and the stop effective potential. So at a critical temperature of the electroweak phase transition, both actions are infinite. We decrease the temperature, we arrive to the temperature at which the critical temperature of the color breaking phase transition. In this case, the corresponding action of the bubble of the color breaking phase transition is infinite, while here we have a finite value of the action for the electroweak breaking phase transition. We decrease the temperature, and we arrive at the nucleation temperature of the electroweak phase transition. And we observe that at this point, the color breaking phase transition is the action of the color breaking phase transition is large.
And you say the bump in the stop direction is huge, so this is why it's really mega stable.
Yeah. And after we arrive to sorry, I didn't say, but this line, the upper line is yes, and the other one is the end of the phase transition. Okay. So we observe that we have checked that for this value.
Very dangerous.
Yeah. But in any case,
Maybe it's a better road.
okay. In any case, we can change a bit this value in order to enlarge this difference, and the windows are not affected too much. Okay? More or less, the result is stable. More or less.
So this 1.6 is more or less dictated by the expanding rate of the universe, right?
In which sense? No, this value.
Well, the beginning and end of nucleation, basically. No?
Yeah, it is in order to have the nuclear. Yeah, but it is the expansion of the universe and the size of the barrier.
Okay. Also the barrier.
Okay, so you can observe already here that just a few GV, sorry, after the electroweak phase, after the critical temperature, the electroweak breaking minimum is metastable. In particular, this is the previous plot. This is the Higgs potential, the subpotential at the nucleation temperature at 80 GeV and at 0 temperature. Okay, we continue to see that this minimum is metastable. We calculated the bounce from, in other words, the tunneling, okay, from all this point to the color breaking minimum, and we discovered that the action of these bubbles is always too large. So the electroweak breaking minimum is stable.
Did you also look now? This is all thermal tunneling, I suppose.
Sorry?
That is all thermal tunneling, but yeah, it's S.
Yeah, the O4 symmetry is below. Are you speaking about the bubbles O4, no?
Well, I'm quantum tunneling, yes, the
Yeah.
four-dimensional one, so they've also checked that.
Yeah. So, okay, another thing is here, from this plot, we observe that it is the critical temperature, and it was this one, it was, in this case, this plot was done for the nucleation temperature electroweak symmetry breaking. And you can you can check that the condition about the strength of the phase transition is improved by considering the nucleation temperature. In this case, it is 0.9, the X expectation value. Okay.
Okay.
Yeah. Okay. I suppose that you are very tight, so we check that this parameter region is compatible with the gauge coupling unification. In order to do that, okay, only a comment, it is necessary to consider also the two-loop approximation, the two-loop contribution, because they have a large effect in the alpha strong prediction of the model. Okay. So what we see here, I think this is the prediction of alpha strong of this model, these lines. The solid lines are the prediction at loop, and the dashed line at one loop. And for this reason, okay, we can see that the two-loop contribution is important. This band is the value of the experimental value of alpha strong for with considering 2 sigma error. And consider 1 sigma error, we obtain this value for a gluino of 500 GeV, which in this value F tilde is compatible with the windows we calculated before. And for gluinos of 100 at the electroweak scale, we decrease the value of M tilde.
But you're not really working. Are you working in M sugra or no?
No.
Not really.
I'm pushing.
So where does this gauge unification come from then?
Yeah. simply because consider the two-loop approximation, we run up the G1 and G2.
Yeah, but no, but also G3. I mean,
and we at the scale. Okay, in some sense we are working in H25.
H5.
Yes. Yeah. Because we are imposing that at MGAT, G strong is equal to G1 and G2.
Yes.
Okay, and after we are.
But is this an M5, H5 experimentally reliable? I mean, it should not be, right?
Okay.
I mean, it will,
As
it
your
will,
five, you don't
it will
have to insist
lead to
on.
proton decay.
Yeah. No. Okay, but. Okay, the aim of this analysis is only to see if what we have obtained is compatible with unification. In particular, all these values depend on, for example, the threshold at the GAT scale.
Yes, but if you are using a different GAT than threshold correction.
Yeah, in fact,
But
So
that's never taken into account in
yes,
these things.
that's,
No?
but you are right, in the sense that the contribution could be important. For example,
At that level of accuracy, I think so. No?
but it is too model dependent.
You see, this is a strange thing many people do. that they consider the running at a very high accuracy, like 2 or 3 loops. But then, of course, as you said, you have these uncertainties coming from threshold corrections at the high scale, which are bigger than, which is an uncertainty which is
The same order.
Yes, at least.
Yes, but moreover, for example, playing with the electroweak parameters, for example, the mu value, or if you change that beta in 3, these lines change. Okay, so the aim of this analysis is only to see that our windows are compatible. It's compatible. Okay, are not ruled out by unification.
Mm. So the rough picture remains. Yes.
Yeah, exactly. So yeah, but you already know. Basically, the most important result is this one: this upper bounds on the X mass and the stop mass, and this one, in the sense that we are predicting a value of the EV scalar, which is larger than 7 TeV. And I think that I have to.
But you had, in your plot, more MH was like 124 experiments. So you said this is some kind of uncertainty, right?
Yeah, it is obtained. Okay, these are considering the uncertainty of 3 TeV, which is only an estimate.
Yes, I propose the following. We stop here and chat a little bit, and I don't know, I would be interested in the second part. So we could, I don't know, maybe we could, in 15 minutes we could just do, I don't know, quickly, I could flash through the slides.
Yes.
Stefan. Yeah. Maybe he can bring it tomorrow.